Thanks so much for the organizers for putting this together. I'm excited to be here and share my work on children's compositional reasoning about numbers. All of this work was done in collaboration with my PhD advisor, Liz Pelkey. And I'm recovering from a cough, so just in case there are any interruptions due to that, apologies in advance. All right. Natural number concepts underlie many of our everyday activities. For example, they help us measure time so we can precisely track when 20 minutes have passed since I started my talk. They help us measure space, such as the lengths of the rooms that all of you might be in. And they help us count things, such as the number of people in this session. While for us as adults, natural number concepts may seem natural now, it takes children many years to learn the number symbols and the words that represent them. So today in this talk, I will present two studies. First, I will present evidence that speaks to whether language shapes children's learning of the number system. And second, I will present evidence that speaks to what kind of training fosters children's learning of the number system. All right, so part one, does language shape children's learning of the number system? The symbol systems that represent natural numbers are compositional. So for example, just 9 symbols along with some power of the base 10 can generate all natural numbers, such that a large number like 234 is 2 hundreds, 3 tens, and 4 ones. I will refer to this understanding that larger numbers are composed from sets of tens and ones as base 10 compositionality. So while the system allows us to combine a finite set of symbols to have unbounded abilities to calculate and quantify the world around us, it can be challenging for children to learn. So one reason is that while the Hindu-Arabic system is consistent in how the symbols combine to represent base 10 compositionality, number words in all languages are not consistent in revealing base 10 compositionality. For example, in English, number words like 11 and 12 do not transparently reveal how sets of tens and ones combine to generate them. But not all languages are the same. So languages vary in how transparently they reveal the base 10 compositional number system. So for example, Mandarin has transparent number words for 12, which is just a combination of 10, 2, as well as 20. So it's different from English. But does this variation in languages affect children's numerical skills, right? So some past work has found that children who speak Mandarin in China, represented by this line, count much higher than their English-speaking peers at the ages of 4 and 5 who are represented using this line. And past work comparing transparent East Asian languages like Mandarin and non-transparent Western languages like English have found mixed evidence for the impact of number naming systems on children's base 10 understanding. So while some studies have found no difference, some others have found that children who speak transparent East Asian languages are more likely to use 2 bars of 10 and 5 ones to represent the number 25, as compared to children who speak non-transparent languages like English, who tend to use 25 single cubes to represent the double-digit number 25. So we built on this prior literature and re-examined the effects of number naming systems on children's numerical skills by including an understudied language, Turkish. So Turkish differs from English in interesting ways. So Turkish has transparent teens, just like Mandarin. So for example, the number word for 12 is a combination of 10, 2, whereas Turkish has non-transparent decades. So for example, 20 has nothing to do with 2, 10, or 50, again, has nothing to do with 5, 10. So it has non-transparent decades as compared to English. Therefore, studying Turkish allowed us to test whether the position that the non-transparent number words occupy in the count list affects base 10 understanding. So if the non-transparent teens are a bigger impediment to counting and base 10 understanding, then Turkish-speaking children should outperform English-speaking children in numerical tasks. But if the non-transparent decades in Turkish are a bigger impediment, then English-speaking children should outperform Turkish-speaking children in our numerical tasks. So now I'm moving to the experiment and showing you what tasks children completed. So the first is a verbal counting task where we ask children to start counting. And when they stop, we give them a series of cues. So first we say, can you keep going? And the next cue is, let's say they stop at 17, we say, what comes after 17? And then if they still can't continue or make a mistake, we provide the previous two number words in rising intonation. So we go 15, 16, 17, and see if they can continue. And finally, if they cannot, we provide them with the next number word, which would be 18, and see how high they can count after that next number word. And then we also administered a base 10 task. Similar to previous studies that use bars of tens and ones, we used large bags and small bags. And we told children that large bags like this that are opaque contain 10 cookies inside and they've already been counted for them. And then small bags like this contain 1 cookie inside. And in order to do the task, we introduced them to a cookie shop where cookies are sold in these large bags of 10 and then small bags containing 1 cookie. And this task had 3 parts. So the first one was comparing sets of quantities represented using tens and ones and judging which one is more. So is this set more than this set? The second is counting the number of bags and saying how many there are in total. So in order to do this, children would have to count both by tens and ones. So they would go 10, 20, 30, 40, and 44. And then the final one was decomposing double-digit numbers. So let's say a customer comes to the shop and asks for 51 cookies. How many large bags and how many small bags should you give them? So in this case, it would be 5 large bags and 1 small bag. All right, so the sample size in this study was 287, and these tasks were administered on 4 to 7-year-old children. They were roughly equal between 3 languages, English, Mandarin, and Turkish. So first, let's look at whether language affects children's counting skills. So here on the x-axis, I have age in months, and on the y-axis, I have children's count range. That is, how high they count before we provide them with the next number word. And here are the results. So what we found is that Mandarin-speaking children who are in this blue line count higher than English-speaking children, and English-speaking children in turn count higher than Turkish-speaking children. And all the dots on the graph are individual data points. And now I'm just going to show you a different graph. So where do children stop in the counting task, right? When we ask them to start counting, where do they stop or make their first mistake? So on the x-axis here, I have language, which is English, Mandarin, and Turkish. And on the y-axis, it's the percentage of children that stop at a particular point. And I'll go over the legend. So if they stop before 10, it would be in blue, but we don't have any English-speaking children who stop before 10. If they stop in the teens, it's in the yellow bar here. And then if they stop between decades, so that is between 21 and 28 or 31 and 38, it would be in this orange part. And then before a decade would be numbers like 19, 29, 39, so right before a decade. And this is if children are able to count 100 and beyond. So there's a lot of information on these graphs, but for the sake of time, the main point that I want you to take away from this is that if the non-transparent decades in Turkish were an impediment to counting, then a higher percentage of Turkish-speaking children should stop right before a decade. But that doesn't seem to be the case because that percentage is similar to English-speaking children. And more importantly, even a large percentage of Mandarin-speaking children stop right before a decade, suggesting that extracting the base 10 rules in the count list might be hard, even when the number words make it more transparent. All right, and then now, does language affect children's base 10 understanding? So here we have age in months, and then on the y-axis, I have the base 10 score, which is the percentage correct across the 3 base 10 tasks that I showed you. So what we found here is that Mandarin-speaking children perform better than English-speaking children, but they improve at similar rates with age, whereas Turkish-speaking children improve at a slower rate with age. These are all descriptive trends, but we confirm these with trends with statistical analyses as well that I'm skipping for now. And here is the same data plotted by children's count range. So now on the x-axis we have count range, and on the y-axis we have children's base 10 score. So when we plot it by count range, we see that the differences between English and Turkish speaking children don't exist, but Mandarin speaking children still continue to do better at similar count ranges. So to summarize the results of part 1, we found that there are differences in children's counting skills by language. However, the stopping points in where children stop when they count suggest that they're not just driven by language. The differences in base 10 task might also not be driven by the transparency of language alone. And this is because Turkish and English speaking children perform similarly when they're matched for count range. And I didn't have the time to get into this, but this is a part of a larger project. And we found that Turkish speaking children had lower performance on another numerical task that doesn't require the precise understanding of number words as composed of sets of tens and ones. So this suggests that whatever differences we might be seeing between English and Turkish speaking children, they might not be driven by language alone. All right. A limitation of the previous study is that the English, Mandarin, and Turkish speaking children all come from different countries. So a lot of other things like education and practices at home could co-vary with a language, accounting for any numerical differences in the tasks. So in order to address that limitation, we conducted a second study with children in India who spoke different languages, Hindi and Tamil. So by studying children within India, we were able to ensure that the children that we recruited attended similar schools that followed the same national curriculum. And we also ensured that children's socioeconomic backgrounds were similar in this study. So Hindi is an extremely irregular language where not just the numbers in the teens and decades are irregular, but the numbers even between the decades, like 25 and 52, are irregular. Whereas Tamil is a highly regular and transparent language, much like Mandarin. So we compared Hindi, an extremely irregular language, with a language like Tamil, which is similar to Mandarin. So if language shapes children's numerical understanding even after accounting for children's educational and SES backgrounds, then we should see Tamil-speaking children outperforming Hindi-speaking children in all our numerical tasks. So the age of children in the study was 5 to 8-year-olds, and a sample size was 230, distributed roughly equally between the two languages. And children completed the exact same tasks as in our previous study, but they were translated into their language. All right, so for the first question, does language affect children's counting skills? A similar plot here with x-axis having age in months and the y-axis having children's count range. What we found is that Tamil-speaking children improve in their counting skills with age, as represented by this blue line, whereas Hindi-speaking children barely improve in their counting skills with age. And this makes sense because many of the number words need to be rote learned in Hindi because of how irregular they are. And now I'm going to show you the same plot with where do children stop in the counting task. Again, there's a lot of information in the slide, but what I want you to take away from here is that a larger percentage of Hindi-speaking children stop even between the decades, which is in orange, as compared to the Tamil-speaking children. And again, this makes sense because the number words even between the decades are irregular in Hindi. And after we give children the next number word, we calculated how many number words on average they produce. And what we found is that while Hindi-speaking children at all ages produce an average of 2 or fewer number words, Tamil-speaking children at the ages of 6 and 7 produce an average of about 10 number words when we give them the next number word, suggesting that Tamil-speaking children have extracted some rules in the number words to generate the next few numbers. All right, and again here, does language affect children's base 10 understanding? On the x-axis, we have age in months, and on the y-axis, I'm plotting children's base 10 score. So while there are differences initially in children's base 10 scores at the younger ages, the general trend is that Tamil-speaking children improve at a faster rate with age, whereas Hindi-speaking children do not. And when we match kids for count range, if anything, we find the opposite trend in that the Hindi-speaking children in red perform better when matched for children's count range. All right, so to summarize the results, we found that there are differences in children's counting skills by language, and the stopping points in children's counting skills are consistent with the language-specific predictions. And the differences in the base 10 task might not be driven by language alone, because Hindi-speaking children have higher scores as compared to Tamil-speaking children when matched for count range. And just to summarize the results of this first study, does language shape children's learning of the number system? Yes, for counting skills, but the differences in understanding of base 10 compositionality might not be driven by language alone. And base 10 compositionality is hard, even when number naming systems are more transparent, highlighting the need for effective interventions to teach children this concept. So that brings us to part 2. What kind of training fosters children's learning of the symbolic compositional number system? First, I want to highlight the challenges that children might face in learning the base 10 compositional number system. One is mastering opaque symbol systems. So while Hindu Arabic numerals are consistent in revealing base 10 compositionality, their understanding depends upon knowing place values. So 3 refers to different magnitudes in 23 versus 32. And place value increases from left to right, which is the opposite of conventional ordering of numerals on a ruler, which is right to left. So this might be counterintuitive and hard for children to understand. And the second is the number words, which can be difficult for children to understand, especially when they don't reveal how they split into sets of tens and ones. The other challenge with understanding base 10 compositionality is representing the same concept in multiple ways. So in order to perform the algorithms of arithmetic, like borrowing and carrying, children need to be able to represent a single 10 both as a set of 10 as 10 ones, and flexibly switch between these two representations to perform arithmetic, which can be challenging for children. So building upon past interventions that use these kinds of blocks to help children learn numerical concepts, and also use board games to help children learn numerical concepts, we designed and evaluated a novel game called Find and Move. So in this game, children play with a board that goes from 1 to 50, and they also have certain cards. So what children need to do is count the number of dots that there are on this card and find that number on the board. So in order to do this, the dots are grouped by 10. So they would go 10, 20, 21, 22, 23, and find that number on the board. And in the next set of cards, children would first find a number like 2 and then add the number in pink to it, like 10. And children were shown the equivalence of adding 10 by moving 10 spaces to the right, or just jumping up the line from where they are. So they could choose to use that strategy if they wanted to play the game more efficiently. And finally, the most difficult kind of card in this game would be a double-digit number that has both a tens and a ones digit. So they would have to decompose 21 into 2 tens and 1 to make efficient moves on the board. So for example, they first find the number in black, 24, and then jump up the board by 2 tens and add 1 to reach 45. So we introduced children to this game and evaluated it using a home-based intervention. So first, all children came to the lab and completed a pre-test that measured their numerical and social cognitive skills. And then they played either this assigned game, the number game that I just showed you, or an active controlled social cognitive game at home with their caregiver for 2 to 3 weeks. And then they came back for a post-test that again measured their numerical and social cognitive skills. The age of children was about 5 years, and they were all from the greater Boston area. The sample size was 48 with 24 kids in each condition. All right. So do children who play the number game find and move improve more in their number scores? So on the x-axis here, we have time, which is pre-test or post-test. And on the y-axis, it's the number composite score, so which is the average of the performance correct or performance on all of the numerical tests. So it's average of the percentage correct transformed into z-scores. So we found that children who played the number game at home improved more in their numerical skills as compared to children who played the social cognitive game. So there was a positive effect of this numerical intervention. And we also replicated this study using a larger board with numbers that go from 1 to 99. And we also changed the structure of the board such that the tens align on the left. And for the sake of time, we just will show the results from this replication as well that showed that children in the number condition improve more in their numerical skills. All right, and to summarize, what kind of training fosters children's learning of the symbolic number system? So we found that game-based interventions that focus on base 10 compositionality and that use multiple representations like a board, group dots, number symbols, and words that all make some aspect of the compositional number system explicit help children in learning this system. So to summarize, in part 1, I showed evidence that language does not strongly influence children's learning of the compositional number system, and some aspects of it might be hard, even when children speak languages that have transparent number words. And then in the second study, I showed evidence that training based on compositionality using multiple representations fosters children's learning of the number system. With that, I want to thank all the children who participated in these studies, all my collaborators who worked hard with me on this research, and all my mentees. And once again, thank you all for listening.